if you recall, we want to talk about flux integrals. These are integrals that we're going to apply to a vector field, although we're going to look at something a little different than we did with line integrals. We want to imagine, for a flux integral, we want to imagine a vector field flowing through a surface. The vector field is going to be like the flow of water or the flow of air. And we want to set up a surface in that vector field. And we want to see how much of the vector field is flowing through that surface. So the context that we set up last time is that the vector field would be the, say, speed of water or air. We can imagine the vector field as being a speed of the air. No, I should say velocity because it's going to have direction because it's a vector field. So let's call it the velocity. Suppose I could generalize this to the velocity of the medium. But we don't have a medium. And so if this is going to be measured, this could be measured in, say, meters per second. And is flowing through a surface, which is some area in square meters. So at each point, we're looking at how fast the water is going through how big of a space. And when we multiply these two things, we get the flow in volume per unit time. So the dot product, or the product of the vector field through the surface is the flow through the surface. I need to give myself enough space. We'll take meters per second and we'll multiply by seconds. Or sorry, multiply by square meters. So it's telling us how much volume is flowing through per unit time. We look at how fast, let's say the water is going, look at how fast the water is going, multiply that by how much space it's taken up, and that'll give us the volume of the water through the surface per unit time. The base scenario is a constant vector field flowing perpendicular to a flat surface. So the base case our base model will be a constant vector field. Flowing perpendicular to a flat surface. We have a constant vector field flowing perpendicular to a flat surface. Perpendicular and flat surface kind of push together into one. What we want is the angle between the vector field and vectors normal to the surface to be 0 degrees, so that when we multiply using the dot product, the cosine of the angle, or cosine of 0, is equal to 1. And so we don't have to worry about things going through at funky angles. That's why we want perpendicular to a flat surface. So this perpendicular to a flat surface, this is so we can get an angle between the vector field and vectors normal to the surface to be 0. So the angle between the vector field and vectors normal to the surface is 0. So we don't have to, when we multiply by cosine of the angle between the vectors, we have cosine of 0, and that's equal to 1. That's something to simplify the process so we can get our thinking in place. It's the same thing as in physics. When you start doing physics problems, ignoring air resistance and ignoring friction. It simplifies the problem before you complicate the problem. You can add those things back in later, but we want to get the basic ideas now. So we got to throw things slowly so we can ignore air resistance. Oh, so this is us slowing things down. This is us ignoring air resistance, friction. So this is based in multiplication of the vector field flowing through the area. So I have a whole area. And we have a vector field flowing through it. And when the vector field is constant, oh, that one looks a little bit bigger. So if when our vector field is constant, that is the same vector at all points in the area. And it's flowing through perpendicular to this flat surface. All we have to do is multiply. We take the vector, the magnitude of the vector, multiply by the magnitude of the area, and that gives us, and times the cosine of the angle between them, the vector fields, said them, times the cosine of the angle between the vector field and vectors normal to the area of the surface, which is 0 degrees. So the cosine of 0 is 1. I get to just multiply. Take the magnitude of the vector and just multiply by the area. we're just using regular multiplication because the angle between the vector field and vector normal to the surface is equal to 0. So the cosine of theta is 1. So we don't need the cosine in this dot product. Cosine of theta is 1. So I just need to multiply the two magnitudes, and I could just take the same magnitude of the vector field at all the points on the area. That's why we get to multiply, because the vector is the same everywhere. We get to just use multiplication because the vector field is constant. It's the same vector everywhere. That's why we get to multiply. Dang it. I don't know if you can see the cursor in Zoom, but every time I try to let someone in, I have to scroll up there, but it's like really close where you put the cursor and it like brings the drop down. Oh, you want this? I'm like, oh no. So I have to pull the cursor down. You want this? No. So I got to work on my aim. So what we want to do is start varying the vector field. That's the first way we're going to make things continuously variable. So this is calculus class. Anything that's constant will become continuously variable. Remember the overall picture in calculus when we are integrating. We are trying to multiply when one of our factors is continuously variable. We are trying to add over a continuum. The continuously variable is the weird part. We're trying to multiply, but one of the factors is continuously variable. We're trying to add. So where does the plus go? That's why we had to develop all these, like I was there. That's why we had to develop these integration tools. We're examining the boundary between the discrete and the continuous. There's our big idea. So let's upgrade our base model and make the vector field not constant. Yeah. Integration is multiplication, but one of the factors is continuously variable. Integration is addition over a continuum. So they're like, where do we put the plus? And that's the weird question. And so the weird thought is, where does this discrete sum where we have places to put plus, what happens? How do we make that into a continuum where there is nowhere to put the plus? There is no in between. Is everybody okay? So the first thing we're going to do is we're going to make the vector field continuously variable. What happens if we have a different vector at every point on the surface? So I'm going to do 2 entire points, but let's say down here, we have one value of the vector. Put this too far down. But up here, we have a different vector. We're still keeping the surface nice and flat, and we're still running perpendicular through it. We can complicate that later. All we have to do then is upgrade our multiplication to a dot product with a cosine of the angle between. What we're going to do here is we're going to break the surface up into a bunch of small rectangles, like we always do. We're going to assume that the vector field is constant over small bits of the surface. So we use the usual strategy. We're going to assume that the vector field is constant for a small piece of the surface. If the vector field is changing continuously, if the function is continuously variable, then it's not going to change that much over a small region. And we're going to use a small piece of the surface, delta A, or it's going to become dA when I make it infinitely small. Then we're going to do the same thing we always do. We take that small piece and make it infinitely small and just add up more rectangles. So we're going to use this little tiny piece, which is gigantic, but tiny enough. And we're just going to break this surface up into a bunch of small rectangles. And then we'll just add up all of these rectangles. Calculate the flow through each little rectangle, and then just add up the total of all the flow. Otherwise known as the usual plan. What are we going to do for this? Same thing we do for every figure. Break it into pieces, multiply, and then add. Then just use an infinite number of pieces. Then there's the Animaniacs being simple. How about they're trying to take over the world instead of just integrate stuff? Makes it less educational, but way more popular. But I think you all are too young to know about Pinky and the Brain. Anybody here know about Pinky and the Brain? If you don't know about Pinky and the Brain, then you don't know about Animaniacs, and you should know about Animaniacs. Then more usual plan, let the small pieces become infinitely small, and this becomes a definite integral. So we're going to integrate over all the points on the surface, the vector field dot dA. At this point, our job becomes describing what those points are. At this point, our job will become describing what all the points on the surface are. So at this point, our job will be to describe all the points on the surface. If our vector is, our surface is just a rectangle, like I've drawn it here, we just have to write down all the x values and all here, all the z values that are applicable. We evaluate the vector field at all the points in that description. We multiply by the dA, which may turn into what looks like in this case, like a dx dy. And then we're just going to get a double integral. So our job is now to describe all the points on the surface. And evaluate the vector field at all those points. Since dA is a piece of that surface, dA is going to be a little dx times a dy, and we're going to get a double integral. The dA could be dx times dy, or however we are describing the surface. If we're using polar coordinates, then it'll be an r, dr, d theta. However we happen to be describing that surface. But it's the same thing that we always do. Figure out what points we're going to be plugging into the function and set those up in an integral. Say, plug these points in. Any questions? How's everybody okay? Everybody looks so very sad. It is Monday. Monday is the sad day. Is Monday the sad day, or is Monday just kind of the saddest day? I think it depends. I think it kind of depends. It's like for me, Monday is the bad, like work-wise, but on Tuesdays and Thursdays, I have an extra class in the afternoon. I don't know if it's really an extra class. I have another class, my third class, and it's 2 hours long, and it's 3 hours long on Tuesday. It's trigonometry, so it's a fun class at least, but it's like 2 hours long and in the afternoon, and I'm not really built for afternoons. I'm not really built for mornings either. Really, I should only be allowed to teach classes from 9 to 10, and then from like 11 to 12. That would be a reasonable schedule. But anything outside of those 2 hours a day, not really going to be prepared for anything. These are our 2 hours in my schedule, by the way, for which I do not have classes. And I am most decided. I can fake it in the morning, like 8 o'clock. I can kind of get through if I can get enough coffee in beforehand. I mean, I hate to admit that I'm a drug addict, but I mean, let's face it, facts is facts. But giving me a class in the afternoon is just a response. But at least it's trigonometry, so it's kind of a fun class. I don't think anybody else in the room agrees that it's a fun class. And we're doing trig identities right now, so I think they're all mad at me. Yeah. But I mean, it's like, here's a list, and part of it is like, hey, remember sum and difference identities? And how they lead to the double angle identities, and how those lead to the half angle identities, and how those lead to the sum and product identities. And there's like, oh, this seems like a lot. I'm like, well, that's only because it's a lot. You have to remember all of them all the time. Actually, that's the great thing about trig identity because you don't actually have to remember them all, but you do have to remember that they exist. So when you're looking at like cosine squared of theta in an integral, you're like, oh, cosine squared, that's trash in integral. I want to trade that for a cosine of 2 theta, which is trivial in an integral. You know what I mean? But then we kind of lose the overall picture of why we would want to do that, because that's very, very edge case. But I'm like, oh, well, it's useful to replace cosine squared theta with cosine of 2 theta, or specifically a half plus a half cosine of 2 theta for integration purposes. But we forget why that's useful. You know what I mean? Yeah. Yes. And more importantly, you have to know that those kinds of things exist. Because when you get to Calc 2 and the subject comes up, I'm like, oh, hey, remember your double angle identities? And people will be like, oh, I don't know, is there a quiz on double angle identities? No, then yeah, I totally do. When you just pull out your phone, hey Siri, what are the double angle identities? You have to remember that they, oh, sorry, Siri. You have to remember that they exist and that you can go look them up. You don't have to have them on hand. You know what I mean? It's unreasonable in your trig class to have them on hand. You should be allowed a computer and just be able to look shit up. That would make too much sense for, the problem is we're in a nonsensical situation for the most part when we're taking a test. It's like, oh no, you have to remember all this stuff. If you could just use a computer to look things up, you'll use a computer to solve the problem. And they go, dude, that's how shit gets done. That's why we have computers. No, they have to remember it. Meanwhile, find me non-trig teachers, and I'll write down the half angle identity for cosine. Right now, do it right now. Don't look shit up, just write it down. You can't, why do you expect your students to be able to do that? I personally cannot write down the half angle identities without looking them up. I don't remember the double angle identity for sine that's in turn. Oh, wait, no, I do. I know it. 2 tangent theta over 1 plus. Oh shit, I actually do remember that one. I think I got that right. But for the most part, these are all very niche things. And we lose this. This is why this keeps coming up. In case you're wondering why I keep saying this shit, you're like, well, you keep saying this shit. I'm like, well, yeah, because I think this is the important part. This is the thing that you want kind of running through, moving forward. Why do we do trigonometric substitution? At the core, we do trigonometric substitution because exponents don't distribute over sums. We have so much problem with this because exponents don't distribute over sums. And that comes from the fact, and you might not have heard that, but you have seen it. You know what I mean when I say exponents don't distribute over sums? You know what that means? Exponents don't distribute over sums because a lot of times we see things like this, x plus y squared, and people will write x squared plus y squared. But this is missing a whole bunch, right? What's missing here? 2xy. You're missing the O and the I in the FOIL, right? So you need the plus 2xy. So we get this when you multiply this, you got to have this plus 2xy. You got to have the OI. It's not just F and L, it's FOIL. Or if you write it the way I got in the habit of writing it, FIOL, FIOL, but I wrote FL and then OI. Floyd. Fleo is better. But the problem is we get this idea and then we get into calculus and we start seeing this construction, the square root of a quadratic. And we're like, oh yeah, we'll just do this. And it's like, oh, that's not how it works, because this square root is an exponent, and exponents don't distribute over sums. But we didn't imagine, we weren't told that this is an exponent not distributing over a sum. And so when we see this exponent, we're usually not told that radicals are exponents. When we see this exponent being applied to a sum, we still try to distribute it. You know what I mean? We get the form of the distributive property, because we talk about distributive property and it's like, oh, A parentheses B plus C equals ab plus act. And we're like, I'll distribute. But we don't send the message that this is multiplication distributing over addition. That this operation here is multiplication. So when people are like, a natural log of B plus C is ln B, because we stop reading the things and we just start spelling them because we're looking at the form. That's how you can tell. When people just start saying sin, cos, and tan instead of sine, cosine, and tangents, I know that the next thing coming up is they're going to be like, oh, ln B plus C is ln B plus ln C. But this is not multiplication. That's not multiplication, so no, we're not doing the distributive property. This is the whole point of doing trigonometric substitution. This is a really, because of this fact, because exponents don't distribute over sums, this is super inconvenient to have the square root of a quadratic. So trigonometric substitution, the whole point of trigonometric substitution is to take these two terms, combine them into one term, then take the square root of something squared, because that just cancels out. Then the only detail we have to worry about is like, it's technically the absolute value of the thing, but that's not important, right? That makes sense? Were you told when you did trigonometric substitution that the point was two quadratic terms get combined into one term so that you could take the square root of it? That's what's supposed to happen. That's the point of the process. I only theorize that we don't teach the point of the process because I didn't understand the point of the process until I had to start explaining trigonometric substitution to other people. I was like, oh, this is how it works. And then I started wondering, why do we keep doing this? What is the reason behind this exercise? Then I took even more math, and I realized the importance of this particular type of transformation. I started taking the long view. Any questions? Comment? This is why instead of doing lots of fiddly problems where we break things down and do a whole trigonometric substitution where we start off with our x integral, we substitute into a theta integral, and it's the integral of secant cubed. Then we get bogged down in figuring out the integral of secant cubed. I know everybody remembers its parts, and you remember the integral of secant is natural log of secant theta plus tangent theta. I remember it. I know everybody knows that, right? There's no quiz, so just say yes. Yes, totally. But you get bogged down in all these details, and what was the point? The point was why we would do trigonometric substitution. Because we've got two terms where it's really inconvenient. A Pythagorean identity will get us down into one term. Then we can apply the square roots and everything is good. And I can also tell that we don't understand the point of trigonometric substitution because we start doing trigonometric substitution that are set up so that the theta integral is a substitution integral. If the theta integral in trig sub is a substitution integral, we shouldn't be doing trigonometric substitution. And they're like, oh, well, it's just for practice. I'm like, well, that's not the point. You know what I mean? A bit of a tangent, but given the context, a little bit more of a tangent squared plus 1. So it's kind of more of a secant squared to be particular. All right, what we have to do next is think more about this plan, because right now we've got our vector fields going perpendicular through a flat surface. We can take care of the perpendicular and the flat part of the surface by using a vector to describe the surface, and the vector is going to be normal to the surface. It makes sense that we want the vector to be normal to the surface because that's one vector that we can drop into a dot product. We can't go tangent to the surface like we did with a curve Because tangent to the surface is an entire plane. We want to use a normal because that gives us one vector at each point on the surface rather than a whole plane. That's why we had to do the opposite back in line integrals. We needed one vector, the dot product with the vector field. So we just used the direction that the curve was going because normal to the curve was a whole plane. That ain't one vector. One vector. All right, that's going to do it for today. Sorry about the tangents. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. See you Tuesday.